All right, we are back. We are doing chapter 8, hypothesis testing. So let's take a look. What are we doing when we're testing hypotheses? Do you feel lucky, Clint Eastwood? Wow, that's a really old reference. I don't think a lot of you are going to get that. It's more, do you feel unlucky? So what you're doing when you're testing hypotheses, you set a threshold and then you run a statistical test on it, and then you see if it meets that threshold or fails to meet that threshold. And so that's the general idea. Our court systems kind of operate in that. If you notice in court, they find you guilty or they find you not guilty. So the assumption is you're innocent until proven guilty. But if they arrest you and charge you, they think you're guilty. So that's the alternative hypothesis, that you're guilty. If they reject the null, that you're not guilty, then that's you're found guilty if you reject the null hypothesis in that. And so, I mean, sometimes like the papers will write found innocent. They never really find you innocent. There's just not enough proof to show that you're guilty, but they still think you did it. You know, you're not proven innocent. You're set up and said, okay, is he guilty or not guilty? And so those are the two verdicts that can be rendered. Hypothesis testing is very similar. Either we reject the null and make the conclusion of the alternative, or we fail to reject the null. It doesn't mean we don't think that's true, but it's not true at the level of evidence that we need. All right? Okay, so let's take a look here. Testing hypothesis, the idea, state the hypothesis, assume it is true, find a survey, take a statistic related to the hypothesis from a sample. Now, given the hypothesis is true, try to determine how unusual it would be to get like your sample results. If your sample is too unusual, let's say 5% of the time it would happen, less than 5% of the time, then we reject the null and conclude the alternative. If your sample isn't too unusual, then you fail to reject the null and you don't really get to say anything. That's the basic concept. So terminology, statistical hypothesis, conjecture about a population parameter. So we're always making these conjectures about the population. So you're going to see that Greek letter mu a lot. The null hypothesis is noted with an H and then a sub-zero. And then we've got equals or less than or equal to or greater than or equal to, usually for their alternative. Usually with the null, in this book especially, it's equals. I have seen other texts where they sometimes do less than or equal to or greater than or equal to, but there's usually always an equal to in it. Our text usually just sticks with just the equal. The null hypothesis is equal to this. The alternative is either not equal, that makes a two-tailed test, greater than or less than, that makes a one-tailed test. So if I say it less than or equal to, well, obviously this one's equals. Less than or equal to is actually at most. And greater than or equal to is at least. You know, that's opposite of what you really think in your brain, but it'll make more sense when we take a look at some examples. So let's take a look at page 2. State the null and alternative hypothesis in the following situation. A researcher thinks that if expectant mothers use vitamin pills, the birth weight of babies will increase. The average birth weight of the population is 8.6. So then what would be the null and what would be the alternative? So our hypothesis, the null hypothesis, this is H sub 0. That's often read H naught. H naught would be mu is equal to 8.6. That's the population mean. This researcher believes that by taking vitamins, you'll get that average up. So H sub 1, I've seen it H sub A for alternative instead of, this is supposed to be a 0, so that's H naught and that's H1. If you did any physics, anytime you have a starting velocity, it's usually v sub 0, v naught. So that's a math thing. Remember, the sub doesn't have any mathematical meaning. It just means I wanted to use h multiple times. So I could put a 0, a 1, a 2, a 3, a 4. I could put letters, I could put abbreviations down there. Anything I want down there as a sub-heading. So he's thinking the pills are going to make bigger babies. So let's take a look. This is a one-tailed test because it's just greater than, so it's all crowded up on the top end of the test. And then they'll give you a percent, usually like 5% or 1% or 10%. Sometimes I've seen it as high as 20% level. That percent goes, you already know, with a z value in a normal distribution. That z value is sometimes referred to as the critical value. So sometimes you'll see it as CV, sometimes you'll see it as z. We usually don't like to call it z with this. With my examples, I'll usually put CV, the critical value, in that when we find z, we see if the z that we find from our sample ends up in the shaded area or the unshaded area. Shaded area always means reject the null. Unshaded area always means fail to reject the null. All right? So several notes. Unusual samples will be split between two tails. That's called the two-tailed test. This is a one-tailed test. They give me a left-tailed or a right-tailed test. That's obviously a right-tailed test. Reject the claim if it falls into the shaded area. Fail to reject if it falls into the not shaded area. Ooh, a type 1 error. So type 1 and type 2 errors. Reject the null when it is true. That's called a type 1 error. So if on this case, I said, okay, I ended up in the shaded area with my sample and I rejected the null. And so then I concluded that, hey, the pills do make a bigger baby. It's greater than 8.6. But then I came to find that in reality, I somehow did let's say a census of all the population of all the babies, and it turned out to be 8.6 again, or 8.58 or something. Then we created a type 1 error. We rejected the null when we really shouldn't have. All right? The way to reduce a type 1 error is just lower your alpha. So if I want to reduce the chance of a type 1 error, type 1 error chance is always the same as your alpha. So alpha is 5% here. If I make that 1%, I've just reduced the chance of a type 1 error by 4%. If I make it a 0.5% or something like that, type 1 errors are when you reject it all but should not have. A type 2 error then is when you fail to reject it all. We conclude it ends up in the unshaded area. We conclude it's really just the same, that the pills didn't do anything, so we fail to reject it all. But then we do a census and find out, and in fact, the ones that took pills were heavier than 8.6. Then we created a type 2 error. That's when we fail to reject the null, but we should have. So, all right. Smaller you make your probability of a type 2 error, the larger you make the probability of a type 1 error, and vice versa. Okay, so that alpha is a tug of war between whether you're worried about a type 1 or a type 2. All right, more terminology. Level of significance for a hypothesis test. So that's something that we set. That's called our alpha. We set that. The region is the shaded region. Like, so this is considered our alpha region, and then unshaded is the non-alpha. One-tailed test would look like that. Two-tailed test, you just have identical regions on either side. All right? Okay, let's look at page 3, examples. So first, we're going to get drawing a picture. So on every hypothesis test, you are going to do the same 5 steps. In fact, on the last test that we're going to take on chapter 8, 9, and there's a little bit of 10 and 11 that we cover, but I don't know how much of that actually ends up on the test. It'll be on the review. If it's on the review, then it's on the test. But I think 10 and 11 we're just covering, but not evaluating on those. So anyway, it's a 5-step process. But on the test, I'll actually lay out the, state the hypothesis, draw me a picture, figure out the test statistic, the Z or the T, make a conclusion, reject or fail to reject, and then write up the conclusion in terms of the actual problem. And so those are always the 5 steps that we do. And we're going to practice right now on page 3, just doing this first part, or actually the second part, which is drawing the picture. Let's get rid of that stuff. Yeah, that eraser's not working for us. That one's a little more efficient. All right. So here we go. Page 3, letter A. Significance level is 5%. And so let's figure out our critical value. Again, if you want to put a Z there, you can, but it gets a little confusing if you have a Z marked there and then a Z also marked with the test that you do. So when I'm actually doing it, I'll always use CV there, critical value. It's still just a Z score in this case. Sometimes it'll be T depending on our situation. But let me show you what we do, just like what we did already, table F. So we're going to go to table F, our friend table F, and you're going to look up one tail. See that it says one tail or two tails right there, one tail or two tail. And so one tail, and you follow it over to 5%, and you follow it all the way down to Z. And we get a 1.645. So now on our critical value right there, we're going to write 1.645. So that means when I find my Z score, if it's in this shaded area, if it exceeds 1.645 and it's in the shaded area, I reject the null and conclude the alternative. If it's in this unshaded area, if it's 1.1 or something, I fail to reject the null and just conclude that the alternative isn't true. All right? Okay, so let's look. That was a right-tailed test at 5%. Letter B is a right-tailed test at 2%. This one's going to be a little more challenging because that's a weird percent. They don't have that on table F. We can still do it. It's workable. But to find my critical value there, or my Z score, I'm gonna have to kind of reverse look up in the charts that have the Z scores all listed. So we're gonna try to look up this part of it. If that's 2%, then this part of it's 98%. So we're gonna try to look up 0.9800 and then find the Z score that matches with that. That'll be our critical value for this one. So first, we would have went to table F, but that's not gonna work because when I look at table F, there is no 2% across the top. One tail, I got 10% or 5% or 2.5% or 1% or 0.05%. So what we're gonna do is we're gonna pop in here, find 0.9803 right there. 0.9803. And then we follow that over to the left, that's 2.0. And then we follow that up to the top, that's 0.06. So 2.06. is the one that goes with, it isn't actually 0.98, it's 0.9803, but close enough. So that's what we would use for our critical value. For that one, all right? Let's look at C is 10% on the left side. And so that's our critical value. We can use the 10% and look that up on table F, only we're going to have to consider that it's on the left side and we're going to put a negative in front of it. So you can still look it up, 10% significance level, one tail, 10%. You follow it all the way down, and the z-score that is listed is 1.282, but we're going to make it negative 1.282 so that it's, because it's on the low end, not the high end. All right? Left tail, 1%. Again, we could use table F, look that up. So 1%, and our critical value is, again, when we look up 1%, follow it all the way back, it's 2.326, but we're going to make it negative 2.326 so that it goes with the left tail. Now, 1% two-tailed, ooh boy. So again, we can table F that thing, but this time we're going to have to go on the two-tail column, not the one-tail column. So we draw that out. We got shading on both sides. And I put Z instead of critical value. Normally I'll put CV there. Critical value is also acceptable. It is a Z score, so I mean Z is okay. It just, like I said, gets a little confusing when you got a test statistic. So when we go to table F, this time we follow two tails instead of one tail. So two tails, and then follow it over to, what did they want on that one? 1%? 1% two-tailed. So 1% is all the way, we got two tails, and then we follow it all the way to 1%, and then we go all the way down to the bottom. And that's how we get our both of those z-scores. So we don't split the z-scores, we just make it, okay, 2.576, that's a gnat tail, and then negative 2.576, that's a gnat tail. All right? Okay. So then, two-tailed test with 5%. Same dog, different fleas, right? That's just, you're looking at table F. We follow two tails 5%. We'll call it critical value this time. So CV is 1.960, and then also negative 1.960. All right. You're always going to have a two-tailed test if it's not equal to. So if your alternative hypothesis is not equal to, you're always going to have a two-tailed test. If it's just greater than, that would be a right one-tailed test. And if it's less than, that would be a left-tailed one-tailed test. All right? Okay. Let's take a look at a made-up problem. On page 4, so suppose that we have a researcher who thinks the use of zinc supplements shortens the duration of a cold, and we know the average cold lasts 8 days. We give the zinc supplements to a random sample of 36 cold sufferers, and their cold lasts average 7.4 days. The population has a standard deviation of 3 days. Now, be careful, because people do this. They make generalizations and they say, well, 7.4 is less than 8, therefore it worked. Yeah, no. Is it statistically significant at a certain level that we pick? We set that level before we start to see if it's significant. So if we say, well, our significance level is 5%. That means with that standard deviation and that sample size, we have to test to see if it falls into that shaded area of significance or not significant, that it just happened by chance possibly, and that's how we got the lower number. It wasn't the same. So look, we're going to say the mean is equal to 8. Again, I've seen some books go with greater than or equal to 8. Your book pretty much sticks with equals to. I don't think I've seen any where they've used an inequality sign there. And then the alternative hypothesis, we're going to say is less than 8. It's reducing. So it's not equal to. If it was not equal to, that means it would make it away from 8, either high or low. We're trying to lower it, make your colt last shorter, not longer. All right? So then if you draw the picture, that's letter B. We'll put that in. And now they have to give you a significance level to test it at. And they didn't really here. A lot of times with humans and medicines, it's set at 1%. So we're going to say alpha is 1%. That will be given in the actual problem when you're doing these problems yourself. All right? So we look up one-tailed 1% on table F. It says 2.326, but we're going to call it negative because it's on the left side, so negative 2.326. And basically, if we find our z-score, that's our critical value. Z-score. Here, I'll put a little sub-z so you know it's critical value. It's our z-score, but that's the threshold. So if our z-score falls to be less than negative 2.3, negative 2.5, it's significant. If it's anywhere in here, even if it's negative, below the mean, it's negative 2.1 or something, then that's failed to reject. That means it's not statistically significantly different. All right? Oof, that was a lot of words. All right, so this is the reject zone. Reject the null and conclude the alternative, and this is the fail to reject. And then we just basically say, nope, it's still the null. Those pills didn't work. The zinc didn't do enough. All right? So we mark the critical and the uncritical. This is called the critical region. This is the uncritical region. All right, let's find Z. That's letter C was mark it. We did that. That's B and C. Letter D here is calculate Z. So 7.4 minus 8 divided by 3 divided by the square root of 36. Remember, we take the population standard deviation and divide by the square root of our sample size. So it's negative 0.6 over 0.5. You take your calculator, divide that, and that's negative 1.2. Which is not statistically significant. That's letter E, determine whether it lies in the critical region. It does not. If I replicate that drawing, here's our shaded area, and then there's our z-score. Our z-score is negative 1.2. It is outside. It's right here, not inside the shaded area. So that means we failed to reject the null. And so what works into that? Because I've had students say, no, it was less. It's 7.4 on average. Well, it was less for a sample size of 36, but remember, 3 is the amount of variation in the population. So that 3 varies our mean up and down. Then you look at that range. That works into the calculation. And we set, our percentages ahead of time. So be leery if you're ever looking at a study and they have a weird setting. 1% is common, 5% is common, 10% is common, even 20% is common. But if they have something like a 17% or something, that should make you kind of go, what's going on there? Because what I think happened there was they set it at 10%, they got a critical value that created a probability of 16%, and they wanted it to be significant, so they set a threshold of 17, so 16 would fall in the shaded area. So be careful if you see an alpha that's funky. All right, let's get F. State your conclusion in the context of the research study. So we failed to reject the null hypothesis at a 1% level. That we already wrote that. Failed to reject the null at the 1% significance level. So that's sort of like for the researchers. Then I want you to restate it for just regular everyday people. So we conclude the null hypothesis because there's not enough evidence to show that zinc shortens colds. We conclude the average is 8 days, and zinc does not significantly short colds. All right. Our average was less than 8, so people like to argue and say it's short in the cold, it was less than 8. Well, it was only a sample of 36, and there's a standard deviation of 3 days. And so it wasn't significant at the 1% level. It would have been significant at the 20% level, but like I said, we usually don't use those high percentages with people medicine. It's usually 1%. Or even 0.5%, sometimes depending on what kind of medications we're talking. So page 5 then on the notes, steps in traditional hypothesis testing: state the null, sketch it, find the Z, T if necessary, and if we get into chi-square, I'll show you how to do that. That's variance or standard deviation of a normal population. Compute the test value, make your decision to reject or fail to reject, and summarize the results in the terms of the study. All right? Okay. Cool. Next video I'll do is 8.2.